Hello friends, today we are going to discuss the topic properties of gemstones and gem cutting techniques. Introduction. The mineral's composition and crystalline structure impart the various physical properties that characterize each specimen. Knowledge of the properties of gemstones is important for the gem cutter and setter as well as to the consumer who can use that information to care for the gem. A perfect crystal is bounded by plane faces which meet at the angles specific for each kind of material. That is, angle analysis can identify minerals. A crystal may be cleaved in directions related to the external form or to a possible crystal form for the mineral. Sometimes two distinct minerals can have the same chemical composition with their differing properties being due to their different crystal structure. Crystal structure affects mineral properties more than their chemical nature. Examples here include diamond, carbon and cubic, and graphite, which is carbon hexagonal, and calcite, which is trigonal, and aragonite, which is orthorhombic, both forms of calcium carbonate. In this episode, we will discuss 1. Physical properties of gemstone, 2. Optical properties of gemstone, 3. Gem cutting techniques. Physical properties of gemstone. Hardness. Hardness refers to the scratchability of a gem. Hardness is rated on a scale from 1 to 10 called the Mohs scale. The scale is not composed of even steps. The first 8 minerals graduate in hardness on a more or less linear scale, but corundum and diamond are much harder. The distance between 8 and 9 and 9 and 10 is greater than any other hardness steps in the scale. Mohs scale: 1. Talc, 2. Gypsum, 3. Calcite, 4. Fluorite, 5. Apatite, 6. Feldspar, 7. Quartz, 8. Topaz, 9. Corundum, 10. Diamond. Some minerals will have a variation in hardness within one crystal depending on the direction in which it is scratched. Specific gravity. The specific gravity is the measurement of the density of a substance. Scientifically, specific gravity is defined in a ratio of the mass of a given material to the mass of an equal volume of water at 4 degrees centigrade. Most gemstone substances are 2 or 4 times denser than an equal volume of water. Specific gravities are expressed in decimal numbers, for example, 4.00 for corundum, 3.52 for diamond, and 2.72 for quartz. Specific gravities can vary slightly with variations of the trace elements. Cleavage and fracture. Cleavage is the splitting of gems and minerals along one of the planes related to the stone's structure. Crystalline minerals have cleavage and fracture, whereas amorphous or massive stones only fracture. Tenacity or toughness. Tenacity or toughness is the ability of a stone to withstand pressure or impact. Minerals which crumble into small pieces or powder are said to be brittle. If a gem bends but returns to its original position, it is said to be elastic. For example, mica, nephrite, jadeite. These minerals are tough and difficult to break. Magnetism and electricity. Those stones which are attracted by a magnet are considered magnetic, such as magnetite and hematite, which contain iron. Most minerals and gems are poor conductors of electricity. Good natural conductors include native metals and metals with a metallic luster, that is pyrite. Natural blue diamond is a semiconductor. Thermal conductivity. Some stones are good conductors of heat, such as quartz, which draws heat away from the body when held and thus feels cold to the touch. A poor thermal conductor, such as amber, feels warm to the touch because it does not conduct heat away from the body. The surface of a genuine gemstone will demist more rapidly than that of glass or an artificial stone. Crystal systems. Although traditionally crystal systems are not part of the physical properties table of gemstones, but most mineral gemstones are crystalline with their atoms arranged in regular and symmetrical patterns. Crystal systems are classified into 7 different systems according to the minimum symmetry of their faces. First, hexagonal or trigonal. This system shares the same axis of symmetry. Second, monoclinic. The monoclinic system has a minimum symmetry of the 1-2-fold axis. Third, cubic or isometric. Crystals in the cubic systems have the highest symmetry. The minimum symmetry is 4-fold axis. Tetragonal. This system is defined by 1-4-fold axis. Fifth, orthorhombic. The minimum symmetry of this system is 3-fold axis. Triclinic. Crystals of this system have no axis of symmetry. So, gemstones within this system are the least symmetrical. Module 3. Optical properties of gemstone. Color. The color of a gemstone due to one or more or several key factors. A mineral can have its own inherent color due to its basic chemical makeup, ideochromatic, or it can start out as a colorless material and gain its characteristic color from trace impurities, that is allochromatic. The actual color of a gemstone, which is not including any optical effects caused by reflection or refraction, is due to the absorptive and reflective properties of any trace elements and impurities within the crystal. Basic elements such as chromium, copper, iron, manganese, and vanadium absorb and or reflect different wavelengths of the color spectrum, playing an integral part in affecting the color of the mineral. Color in gemstones can be caused by chromophores, which are trace impurities, crystallographic, that is electronic distortions in the stone's matrix, or a combination of both. Chromophores. A chromophore is the part of a molecule responsible for its color. The color arises when a molecule absorbs certain wavelengths of visible light and transmits or reflects others. The chromophore is a region in the molecule where the energy difference between two different molecular orbitals falls within the range of the visible spectrum. Visible light that hits the chromophore can thus be absorbed by exciting an electron from its ground state into an excited state. A chromophore is either an element or physical structure in a substance that produces color. Color centers. Unpaired electrons on non-transition metal ions may also produce colors in certain circumstances. This can either happen due to misplacement of an ion, that is, and an unpaired electron taking its vacancy, or due to the displacement of an electron from, that is, natural or artificial radiation. In both cases, a color center is created and the unpaired electron can be raised to higher energy levels through the absorption of incident light, as with unpaired electrons of the transition metal ions. In the first case, the color center is an electron hole center, and in the latter case, it creates a whole color center. Fluorite is most often used to describe the mechanism of an electron color center. The purple color of fluorite is caused by the absence of a fluorine ion, and an electron is trapped in the vacancy it leaves behind. Whole color centers are usually illustrated by smoky quartz. Luminescence. Luminescence is the phenomenon that shows itself as a glowing of a gemstone. This is caused by absorption of energy and the releasing of surplus of this energy in small amounts. In gemology, we are usually only concerned with the following types of luminescence. They are fluorescence, phosphorescence, triboluminescence, tenebrescence, not technically a luminescence, cathodoluminescence, thermoluminescence. The cause of luminescence are varied but are mostly due to impurities, which are also called activators, or due to defects in the crystal lattice. In general, the presence of iron inside the gemstone kills or suppresses luminescence. Luminescence effects are useful in gemstone identification, especially for differentiating between certain natural and synthetic gems. Iridescence. Iridescence is the property of certain surfaces that appear to change color as the angle of view or the angle of illumination changes. Iridescence is an optical phenomenon of surfaces in which hue changes in proportions to the angles of observation and illumination. It is often caused by multiple reflections from two or more semi-transparent surfaces in which phase shift and interference of the reflections modulates the incidental light. Dispersion. A characteristic refraction or bending is associated with each different wavelength of light, and this separation of white light into component colors is called dispersion. In other words, dispersion is the separation of light into its separate spectral colors. Dispersion is actually measured by subtracting the refractive index of red light from the refractive index of violet light. The gemstone most famous for its dispersion is diamond, but several colored gems are noted for their impressive dispersion, including sphene, demantoid garnet, sphalerite, and zircon. Diamond's dispersion is 0.044, while quartz is 0.013. Diamond is more dispersive than quartz. Inclusions. The internally visible crystals, fractures, bubbles, and other small flaws in a gemstone are referred to as inclusions. Most gemstones have some inclusions that are only visible under magnification. Some have inclusions that are visible with the naked eye. Gemstones that are flawless or that have few flaws will be more expensive. Internal fractures are the most serious because they may adversely affect the durability of a gemstone. But inclusions are not always bad. They can provide a means of identification for some gems and can even indicate the origin of the gem. Alexandrite effect. The term Alexandrite effect is used in gemology to describe a distinct change of color appearance when a gemstone is switched from daylight to incandescent light. Gemstones that exhibit the Alexandrite effect can actually be divided into four categories based upon the value of the calculated absolute hue angle change of the material under different pairs of illuminants. The Alexandrite effect is a non-color constancy phenomenon. It can be explained by a combination of both chromaticity adaptations to the different light sources and vision system responses to the spectral distribution of the light emitted by Alexandrite effect gemstones when they are illuminated alternatively by the different light sources. Pleochroism. Since light waves are absorbed at different rates along different crystal axes of a doubly refractive gemstone, different axes can appear to be different colors. This is called pleochroism. Pleochroic gemstones may have a different color when looked at from different directions. Pleochroism creates unique color qualities in gemstones. It can add the richness of a gemstone. It is necessary to examine pleochroic gemstones at all angles to see the full color potential. This is most obvious when looking at tourmalines and aleucite, where the pleochroic colors are easily observed. Color zoning. The term color zoning refers to the uneven distribution of color within a gemstone. Color zoning is typically due to changing conditions during crystal formation. If the availability of trace elements that serve as coloring agents changes, there will tend to be areas of less or more color in different parts of the crystal. Gems that are not colored by impurities such as peridot and topaz will rarely exhibit color zoning. Color zoning, like inclusions, can be graded on a relative scale. Zoning can be minute or minor, obvious or prominent. The location, color difference, and contrast are also important factors. Many natural gems will exhibit some degree of color zoning, and this is an important sign of their natural origins. Catuency. Catuency is a special optical phenomenon which is exhibited by some rare gemstones. Due to the reflection of light, the phenomenon catuency took form. The reflection exhibits a single glowing band of light across the surface of a gemstone and helps us to see a silky glow, which is called catuency. The displayed band of light looks like a slit of an eye. A finely marked eye line can be recognized which runs right through the gem. In case of some good specimens, the eye seems to open and close when the gem is rotated. Inclusions of foreign particles in gem are main reason of reflection of light and create the phenomenon catuency. The reflective inclusions of fibrous particles of foreign minerals in gems should be thin, needle-like parallel orientation. Sometimes occurrence of hollow tubes in parallel orientation is the reason of silky radiance of gems, which is known as catuency. There is another factor also. The inclusion of cat's eye gems are not well organized, scattered randomly. Asterism. The ability of a gemstone to show a star is called asterism. Asterism is caused by the dense inclusions of tiny fibers of foreign minerals in gems. Generally, these inclusions are the reason of the reflection of light and form a wavy star-like formation which moves around when the mineral is rotated. The inclusions must be long, very thin needle-like, which is called a rutile. Asterism is produced when needles intersect each other in multiple groups. The best way to see the star is to examine the stone using one strong concentrated light source. A pen light is an excellent tool for this. Stars are created by the reflection of light by the inclusions in the stone. The best known examples are the 6 red stars which occur in rubies and sapphires and rarely in spinels. 4 red stars occur in garnets, but they are rare. Quartz may show multiple stars in one stone. Other species may exhibit stars. Gem cutting techniques. There are a number of different ways you can cut gemstones and dozens of resulting shapes. Here are just a few types of gemstone cutting techniques. Cabochon cutting. A cabochon is a polished gemstone with a flat bottom or slightly rounded bottom and a convex or rounded domed top. The traditional cabochon is an oval, but cabochons can also be fashioned into other shapes, including triangles and rectangles. Cabochons, commonly known as cabs, are the oldest and most common form of gem cutting. Gems cut in cabochon are shaped and polished rather than cut. In antiquity, This was generally the only cutting option available other than using the gem with the natural facets of their crystal structure. Cabochons are used for making jewelry, often carved as intaglio or cameo, and are also used in crystal heading. Today, the cabochon cut is applied to gems of limited transparency. For example, turquoise, jade, agate, etc., or as a result of predominate inclusions, or for gems where the cut's carved surface accentuates special characteristics. Faceting. This is the type of cutting where an artisan takes a gemstone and covers it with numerous flat, geometrically arranged surfaces or facets. Faceting is quite challenging from a geometric point of view and requires a great deal of skill. The different facets allow light to enter the jewel at different angles and reflect off the bottom facets. The result is an increased appearance of brilliance. Common faceted gemstone shapes include squares, rectangles, ovals, cushions, shields, hexagons, octagons, rhomboids, and parallelograms. Facets can be straight or curved. Examples of gemstones that are almost always faceted are zultanite, aquamarine, and morganite. Diamond cutting. The most common cut for diamond is the brilliant cut. When correctly cut, it not only produces the best balance of fire and brilliancy, but also enables the best use to be made of the octahedral form of the diamond crystals. The standard brilliant cut consists of 58 facets, 33 on the top or crown of the stone and 25 on the base or pavilion. Modifications of the brilliant cut. There are many modifications of the brilliant cut, both in outline and in the number of facets. Marquise is the name used when the outline is boat-shaped, although navet is used in a similar connection. A pear-shaped outline is called a pendeloque, and an outline which tends to be squarish with rounded corners is termed cushion-shaped. For small diamonds, the single cut or 8 cut is often used and consists of 8 facets surrounding the table and 8 pavilion facets below the girdle. The Swiss cut has 17 facets on the crown and a further 17 facets on the pavilion if there is a culet, for a total of 34 facets. The zircon cut, used extensively for zircon, is characterized by a second set of facets surrounding the culet. For large stones, a greater number of facets than the 58 of a standard brilliant may be put on, but they will still conform to the general symmetry. More elaborate modifications of the brilliant cut are the king cut, which has a 12-sided table with 48 surrounding facets to form the crown of the stone and 37 facets including the culet on the pavilion, for a total of 86 facets in all. The magna cut has a 10-sided table facet surrounded by 60 facets on the crown and 41 facets on the pavilion, making 102 facets in all. New diamond cuts. 5 new diamond cuts, zinnia, sunflower, dahlia, marigold, and fire rose, were developed to better utilize rough that was either irregularly shaped, heavily included, small, or strongly colored. In addition to these new cuts, several other cuts have been developed over the last 25 years. The radian consists of 70 facets and combines a step cut crown with a brilliant cut pavilion for added brilliance. The trilliant radiant cut resembles the trillion but is usually cut with more rounded sides for additional weight retention. The quadrillion cut is square shaped and consists of 49 facets. The princess cut is similar in appearance to the quadrillion but is usually cut with steeper crowns. thicker girdles or deeper pavilions to provide greater yield from the rough. Colored stone cutting. In addition to the cuts already discussed, there are multitudes of other cuts used for colored gemstones. One of the newest cuts to emerge in the marketplace is the fantasy cut, which is used extensively for amethyst, citrine, and blue topaz. Characterized by its irregular form, it is favored particularly by designers who wish to create unique, one-of-a-kind pieces of jewelry. Other favored cuts include the mixed cut, which consists of a brilliant cut crown and a step cut pavilion. The Berrien cut, which was designed to improve the brilliance of square and rectangular stones and consists of 62 facets. The Portuguese cut, which can have up to 177 facets, and the cushion cut, which is a cross between an oval and a rectangle. Summary. Sometimes two distinct minerals can have the same chemical composition with their differing properties being due to their different crystal structure. Crystal structure affects mineral properties more than their chemical nature. The cutting of gemstones is required because many gemstones have a strong and rigid crystalline structure and are too hard and brittle to be shaped any other way. The principle behind gemstone cuts is based on the way the molecules of stones are stacked. The reason for gemstone cuts varies from stone to stone. For the diamond, cutting the gemstone is needed to get the brilliance the diamond is famous for. Other reasons for cutting a gemstone is to achieve a particular shape or style for a specific piece of jewelry. Different cutting styles suit different gems. Transparent specimens like diamond are best faceted, whilst the opaque gems, agate, onyx, turquoise, and malachite are best cut as cabochons or as beads. Cabochons are the oldest and simplest way of cutting gems, and the technique is still popular to this day. Thank you very much.